Hello dear students, welcome you all for the 14th session of JEE Advanced Preparation. That's it YouTube channel. For the last 13 sessions, I tried to give you the maximum input related to the chemistry preparation for the JEE Advanced using the PYQs. You know that every previous year question can be used as a source to learn a new concept, because you all know that the questions that are asked in JEE Advanced themselves are very interesting and thought provoking. Now you have solved so many questions so far from the physical general chemistry as well as organic chemistry, and I had also finished the S block elements, P block elements in my previous sessions. Now we have entered into the unit where the questions were asked from the D&F block elements, the coordination compounds, metallurgy and salt analysis. Indeed, majority of the questions which were asked in inorganic chemistry are from these chapters. And you know that there is a unique link between chapter to chapter. There are a huge number of questions that were asked in the previous JEE sessions. So I had made these chapters into 2 units. So in session 14 we are going to cover up 1 unit, and then in the last session we are going to cover up the next. So let's get into the questions, right? We will see the question from the complexes first, alright, and then we will move on to the other type of questions. Let's see the first question. Alright, you have to find out the set of the compounds which are exhibiting sp3 hybridization and thus showing the tetrahedral geometry. You can see that you are given the atomic numbers of all the elements which are the central metal atoms of these complexes. You can see that every time when you are given the complex, you need to write the valence configuration. Over here the oxidation state of iron is +3, alright. In the second compound the oxidation state is -2 because carbonyl group is neutral. You can see in option B it is cobalt -1, and in option B the second compound is cobalt +2. Option C has nickel 0 and the other compound has nickel in +2 oxidation state. Copper +1 because pyridine is a neutral ligand, and in the other complex it is also, you can see Cu cyanide complex, so it is also +1. After taking this, you can apply valence bond theory to solve this question. CFT, that is crystal field theory, is not required. Alright, so you can see that the total electrons that are actually with the iron are 26. That means you are going to write it as argon, 18 electrons, then 3d6 and 4s2, out of which you have removed 3 electrons, isn't it? You can see that you have removed 3 electrons. So what is that you have left out? 2 electrons have gone from here and 1 has gone from here, so you have the d5 configuration, alright, isn't it? If it is Fe -2, you know that you are going to write it as what? 3d7 and 4s2, because you are adding 2 more electrons into the central metal atom. Likewise, you write or fill the electronic configuration of all. You can see that this is 27 means argon, 3d7, 4s2, 18 +2 and then 7. Now you can see that you have total 20 for the cobalt. You have 28 electrons, hence you are going to write this, alright, isn't it? 18 +2, and then you are going to add 1 more electron, that this will become 3d8, right? So this will become what? 3d8 and 4s2. Over here cobalt is +2, that means you are going to remove these electrons, so you are going to write only 3d7. So first you need to write the configuration. Nickel is 28, so 3d8, 4s2, and these electrons are removed here, it is 3d8. So this is how we are going to write, right? This is 3d10 and this is also 3d10. First you have to write the configuration, isn't it? After that you see, you need to check what kind of ligand is associated with it. You can see that this chlorine is weak field ligand and carbonyl is strong field ligand. Likewise you categorize, strong field ligand, weak field ligand, strong field ligand, strong field ligand. Alright, so this is strong field ligand. Pyridine is weak field ligand. It is moderate, it is neither weak nor strong. You have to take up to ammonia as the strong field ligands, where the pairing energy would be greater, isn't it? Now you see that since you have been given that 3d5, that you are going to write as 3d5, 4s0 and 4p0. Alright. I am going to divide this neatly so that there is no chaos, isn't it? Let's check. There are 5 electrons initially arranged in the iron. Alright. And you can see that it's a weak field ligand, so no pairing would take place, right? So all the orbitals that are vacant can be arranged for the lone pair donation from 4 ligands that are chlorines, right? So hybridization is what? sp3, isn't it? Over here you have taken up the strong field ligand. When you take strong field ligand, the pairing energy is greater than the crystal field splitting energy. Therefore, the electron would get paired up. So what will happen here? The rearrangement of the electronic configuration will take place. That means these 2 electrons will go into this, giving rise to 5, 6 and then 7. You can see that 2 more electrons have been added from the S, isn't it? So this is completely almost full. So 4s is vacant and 4p is also vacant. Therefore this can also be entitled with sp3 hybridization. So these 2 complexes are having sp3, hence they are tetrahedral, isn't it? I hope you understood. Alright. Alright, isn't it? Let's see the next one. CO minus, D8 and 4s2, you have to check the ligand. Here you can see it's a strong field ligand. So strong field ligand will pair up the electrons, so this will become what? 3d10. After the rearrangement, 4s0 and 4p0. Once again the 4 orbitals are vacant, hence this is also sp3 hybridized. Then next is CO plus 2, 3d7. Alright, so no pairing would take place with the weak field ligand. So 7 electrons are intact. Alright, you are going to write 7 electrons intact, not going to rearrange. So your 4s is vacant and 4p is vacant, so this is also sp3. Over here you can see, since you have taken the strong field ligand, the pairing would take place, isn't it? Now what will happen here, that the 2 electrons also will be added into this, giving rise to 3d10 configuration. So 4s0 and then 4p is also vacant. So this is also sp3 hybridized. Alright, so you can see nickel plus 2, that means you have only 3d8 electrons. So what will happen if you take the strong field ligand, that is cyanide ion, the pairing will take place. So when pairing occurs, you can see that there is one s orbital from the inner, there is one d orbital from the inner orbit is vacant. Therefore it will take the dsp2 hybridization for the filling of electrons by the strong field ligand. So the hybridization of this complex in nickel tetracyanide is actually dsp2. If it is dsp2, then geometry is what? Square planar. So this is not matching to our requirement. This has matched. Over here also you can see whether I take strong field ligand or weak field ligand, doesn't matter because already the orbitals are full. Therefore only the possibility is nothing but sp3 hybridization over here, right? Because whether you take, there's no scope of any pairing, no. Therefore this is sp3, this is also sp3. So you can see that this is also having sp3 hybridization, means tetrahedral. So right answer for this question is A, B and D, but not C. Important frequently asked complexes. Please repeatedly, you have to understand that repeatedly these complexes are only asked, so emphasize more on these complexes. Now let's see the next question. You can see interesting matching, multiple matching. You can see the options, right? The same thing, it's a strong field ligand, and you can see the chromium, and atomic number of chromium is 24. All right, so you're going to write it as what? Argon 3d5 4s1 is the general electronic configuration. However, here you can see chromium is present in its +2 oxidation state. Therefore, rearranged electronic configuration of the chromium will be 3d4 4s0, isn't it? Now you can see that over here d4 configuration is there. So you can see that 1 is having what? T4 configuration. So you can see that 1 is having linkage with T. So I will rule out this B and C because 1 is having the linkage with T. Then I will check only for the other option. If I am right, then it's going to be wonderful, right? You can see that you have taken a strong field ligand. So it's obvious that the pairing of electron would take place. Over here, what will happen? One electron will come over here, only one electron, remember my friends, okay? Then it will vacate d2 sp3 orbitals for the hybridization. So when electrons are pairing up because of the presence of strong field ligand, you know that low spin complex, because electron pairs up, spin decreases. So you can see that it is matching with R. Alright, and you can see that the number of unpaired electrons after the pairing up are left out to be only 2. So n equal to only 2 over here, I am going to write here. So mu will be under root of 2 into 2 plus 2, that is not this, therefore this is ruled out. So anyways you got the answer, but still you have to check it, isn't it? Now we can see that what else is given? Ruthenium, isn't it? Ruthenium is the complex which is being mentioned. Ruthenium, you want to check that ruthenium, you can check, or you can do the remaining, right? Ruthenium, I'm going to write it here, is actually 47 5s1 5p0. Alright, so what is the oxidation number? Ruthenium plus 4. So you're going to remove 4 electrons from that, so it's going to be what? 4d, 1 from here, and this d4 5s0 5p0. So you can see that ruthenium is also having d4 configuration, so this is also matching. Ruthenium 2 is matching to what? Is it d4? P and S, no? So you can see, yeah, we will check anyways we got the answer, so it's not so worry. Metal ion is in +4 oxidation state. You can see this is matching with S, and let's check the T2G orbital arrangement. You can see that there is a weak field ligand which is being taken over here. Therefore pairing energy is less than delta naught, isn't it? Electron doesn't get paired up. Alright, so what will happen here? The electronic configuration tends to be what? T2G 4, and total electrons are this thing, right? 0. So you may be wondering, sir, how come the pairing is not taking place? Is taking place here. You can see that 4 electrons, right? So you would have kept actually 3 and 1 here because this delta naught is less. However, the delta naught value, please understand here this point very clearly, that this delta naught value is high for the reason that it has more positive charge. This is one of the important aspect of complexes. More positive charge is making this delta naught split a lot, and then pairing had taken place. So the electronic configuration is T2G4 and EG0. So 2 is matching with what? P. Then 3 is Q and T. You can check out, right? 3 chromium plus 2. I'm writing 3 over here, chromium plus 2. that is 3d4 configuration. Alright, so T is matching for 3, and what about Q? You have to check, because it's weak field ligand, no pairing would take place. So N is equal to 4, therefore mu value is under root of 4 into 4 plus 2, that is 4 point something. So this is also matching, isn't it? So fourth option, iron plus 2, you have to check iron plus 2 configuration is what? 3d6, 4s0, and then 4p0. You have to check the ligand. You have the weak field ligand only here also. So what's happening here? No pairing would occur. Alright. So what else? Number of unpaired electrons are 4. So Q is also matching. Mu value is under root of 4 into 4 plus 2. And then what about P? You can see that yes, there is no pairing. Alright. So the configuration is that mu is matching, and then what else? P comma Q, isn't it, right? So T to J orbital, total 6 electrons need to be filled. The electronic configuration of iron is this thing, right? So right option is option A. Next, let's see the other question. So platinum complex, isn't it? Total number of possible isomers. First you have to write the structural, and from there you go to the stereoisomers. You have to write both, because total number of possible means you have to consider both. You can see you're going to write PTNS3 taken for Cl2 Br2. Since you have got the ionization possible, you can write PTNS3 taken for Br2 and Cl2 outside. And there is another possibility that you can keep one chlorine inside, one bromine inside, and the other two combinations outside. So you'll be getting what? Br and Cl outside. So these are the ionization isomers possible. And you have studied that MA4B2, this type of complex, show geometrical isomers, isn't it? This is showing what? The geometrical isomers, and that means what? It can be written as what? This cis and trans. So everything, right? This is also MA4B2, this MA4BC. So this also shows cis plus trans isomerism. This also shows cis plus trans isomerism. When you write any isomer randomly, you can see there is A4B2, there is a plane of symmetry over here. So this tends to be what? Achiral. Alright, so total number of geometrical isomers are, you must write 6, isn't it? Let's see the next question. The spin only magnetic moment is asked for chromium plus 3, and you can see copper, what is that? Plus 3 in Bohr magnet. It's a relatively easier question. You should write the electronic configuration of chromium as, right, argon. Total number of electrons over here are 24, here are 29. You're going to write it as 3d5, 4s1 initially, isn't it? But you are to remove 3 electrons, so you're going to remove 1 from here and 2 from here. So what's left out totally? 3d3. Over here you're going to write it as what? 3d10, 4s1, isn't it? Now since copper is an exceptional case, copper is actually what? Plus 3 oxidation state over here. So you're going to remove 1 from here and 2 from here, isn't it? That means 3d8. Alright, isn't it? So 18 plus 3, 21, because you have removed 3 out of 24. You can see 18 plus 8, 26, because you have removed 3 from here. So you can see that you have taken strong field ligand and weak field ligand. So if it is strong field ligand, the pairing might occur if there is any possibility. If there is no possibility, it won't occur. You have to check on the possibility also. Watch out carefully. You can see that there are 3 electrons here. Alright, there are 8 electrons here. So here you can see that n value, because the weak field ligand, no pairing occurs here, right? Weak field ligand, no pairing. Strong field ligand, pairing. Okay. So here you can see that n equal to 2. That is number of unpaired electron. Alright. So any mistake? Chromium is what? 3d5 4s1 and it is plus 3. So here you can see that n equal to 3. So mu value equal to here under root of 3 into 3 plus 2, that is 3 point something. Mu value over here equal to under root of 2 into 2 plus 2, that is 2 point something. So option A, isn't it? Easy question relatively. So such type of question we don't usually anticipate in advanced exam. You can see that this is iron, what you call plus 3 configuration, and you have to write all possible cases here. You have to sort out each and every option, right? You can see that iron is plus 3. It's a weak field ligand. So plus 3 means 3d5, 4 is 0, 4p 0, isn't it? So use VBT for hybridization. Don't go for CFT. You don't require it. Alright. And weak field ligand, no pairing would occur. Therefore, hybridization, that the empty orbitals are what? sp3. So option A seems to be correct. Let's check out the option B. You can see CO at the middle, octahedral geometry, because coordination number is 6. So I'm going to fix up this ethylene diamine and I'm going to write 2 ammonias and 2 chlorines adjacent to each other, and accordingly I'm going to write the structures here. All possible structures I am writing. Isn't it? So I am fixing up something that is nothing but ethylene diamine, and I am going to write the remaining. What else you can write? You can keep NF3's opposite, chlorines beside, or you can keep Cl's opposite, NS3's beside. And what is the other possibility? The total 4 isomers that are possible here. You can keep NS3Cl, NS3Cl. So it has 2 geometrical isomers. Is a wrong statement. So total number of isomers possible are 4, isn't it? So you can see that FeCl4 minus has higher spin, only magnetic moment than. So I'm not going to do that anyways. I have explained you how to do that. You can see here this has the strong field ligand, that is ethylene diamine, that there is a scope of pairing of electrons. So if there is pairing, then spin will decrease. So this is the simplest logical, and however you can see that this is a weak field ligand, no pairing. So might be, I'm just checking on the possibility that the spin is high. So this may be the right answer. I want you to check out, right? So cobalt, you have to check it again, right? So you have to write the oxidation numbers. Cobalt is plus 3. And cobalt actually 3d7, but it will become what? d6. Because you have removed 2 electrons from 4s and 1 electron from 3d, isn't it? So 3d6, 4s0, 4p0, 4d0. Alright. So repeatedly same questions I am discussing, similar questions I am discussing, isn't it? You can see that 6 electrons here, 0 electrons here, right? So you can see that cobalt ion in this is showing sp3d2 might be a wrong answer, for the reason that you can see we have taken strong field ligand. You have to emphasize on the type of ligand. This is strong field ligand. If it is strong field ligand, pairing would occur. This is the scope of pairing, right? So these two electrons would pair up with these two electrons, leaving inside the inner orbitals, right? D2 sp3 should be the correct answer. So this is also a wrong option. So right answers are A and C for this question. Hope you are following, isn't it? Now let's move on to the questions related to what you call metallurgy, right? Interesting. Now you see the correct option related to the extraction of iron from its ore in the blast furnace operating in the temperature range, right? Upper temperature range and lower temperature range are very important, right? In upper temperature range, carbon monoxide is used as the reducing agent. In the lower temperature range, coke is used as a reducing agent. Very frequently asked question. However, this is different. Limestone is used to remove silicate. Yes, that's true. What will happen there? You know, limestone CaCO3 would be heated to produce what? CaO and carbon dioxide, right? So this CaO is going to react with SiO2 to give you CaSiO3, and this will be removed as slag, isn't it? So option A is correct. Yes, 4% is there in pig iron, that's true. And option C, yes, option C is also correct, because you know the reaction, very popular reaction between CO2 and C. Exhaust gases consist of NO2. This is wrong, right? From where nitrogen comes. Actually, exhaust gases are CO, CO2, H2O. So this is not the correct answer. So right answer is A, B and C for this question. Alright. Let's see the next extraction process related, right? PBS and PBO. You know that, right? Self reduction for lead as well as copper, very frequently asked, right? So your PBS gets oxidized to PBO and SO2, and this PBS will get reduced by to give you what? PB and SO2. You have to balance the equation, isn't it, right? So this seems to be correct. Option A is correct. Let's check out option B. In the extraction process of copper from copper pyrite, that is CuFeS2, silica is added to produce copper silicate. Silica is added to produce copper silicate. Let's see. When this is oxidized, we will be getting CuS plus Cu2S plus Fes and SO2. So your Cu2S is undergoing self reduction to give you what? Cu plus SO2. So we will see that partial oxidation of sulfide over copper by roasting for self reduction. Yes, that produces, this is called blister copper, right? It will develop the blisters because of the presence of sulfur dioxide. So blisters will be developed. So this is correct. Let's see the other options first. You can see that when this cyanide process very frequently asked, right? Zinc powder is used. What will happen when you are using the zinc powder? Zinc is a very good reducing agent. It is going to replace the gold by itself, right? Plus gold. So gold is extracted by the exchange process, or what you call the cyanide process. So this is correct. Looks to be, this is also correct in the extraction process of copper from copper pyrites, right? Copper pyrites. Silica is used to produce copper silicate. Whatever is produced here, SiO2 gives rise to CuSiO3. This is produced. So I am not very sure, but I think right answer should be ABCD. I want you to just once check. You can see the next question is from salt analysis, and that too very interesting. You can see that you got an aqueous solution of salts is giving rise to white precipitates with either dilute HCl or dilute NaOH, isn't it? Now you can see option A. When I am using HCl, you will be getting PbCl2 plus ZnCl2. When I am using NaOH, you will be getting what? PbOH taken twice and ZnOH taken twice. Alright, so this is soluble. Alright, so this is white. You know that both the substances are white. So you will be getting white precipitate only. Here predominantly the white precipitate is because of this. It is anyway soluble. However, when I am using excess of NaOH, that's not mentioned though. It is also soluble, but still there is a white PPT. Look at the option B. You will be getting PbCl2, you will be getting what? BiCl3. However, you should know that BiCl3 will react with water to give bismuth oil chloride, which is again a white PPT. Alright, so this with HCl is okay, but what about this with NaOH? NaOH is going to give you what? PbOH taken twice plus bismuth hydroxide, both are white. So there is no point that you are getting any other color. Option B is also correct. Let's see option C. Silver hydroxide. Alright, brown colored, you know that upon long standing converts into Ag2O, which is black color. So that ruined the game, right? So with NaOH you won't get the white PPT. Alright, of course with NaCl I think it will happen, with HCl it will happen, but with NaOH it's not happening. So C is ruled out. And what about option D? You can see option D is lead, yeah, that is scattering. But what about Hg? You know that HgOH taken twice is yellow in color. What do you say? And HgCl2 is soluble. So because of this yellow color you won't get white. So right answer for this question should be A and B. Let's see another question from the salt analysis. Salt analysis comprehensively covers all S and P block elements. I want you to revise salt analysis very carefully. So you can see colorless aqueous solution contains the nitrates of two metals X and Y. When it was added to an aqueous solution of NaCl, a white PPT is formed. Whenever I say white, it will be usually silver. Only option is given, right? The precipitate was found to be partly soluble in hot water. Yeah, that's simply true. To give a residue P and a solution Q, right? The residue P was soluble in NH3. That clears the game, right? And also in excess of thiosulfate. The hot solution of Q gives a yellow PPT, right? With yellow PB was. So silver and PB, basic question, right? You can see what's happening is like, you got silver nitrate is added the solution of NaCl to give you what? AgCl. You know that AgCl is soluble in ammonia, but not AgI. Remember this, AgCl is fully soluble in ammonia, AgBr is sparingly soluble, AgI is insoluble. So this is soluble in ammonia. This point is scattered, and you can see that this precipitate was the residue P was and also in excess of S. So what's happening here, that when you take this and when you add what you call Na to S2O3 excess, actually when you add limited you will be getting Ag to S2O3, which is again white PPT. But when this is added excess of Na to S2O3, you have studied, right? Sodium argento thiosulfate. This is soluble. Similarly, you can write the reaction pertaining to that of lead. You know that only one reaction which is helping you out, that PB's nitrate giving rise to PbI2, which is a yellow precipitate. Related to lead, you will get one chromate, the other iodide, which are yellow in color. So do not forget them. It's easy to remember, isn't it? Now we can see the next question. The reaction of potassium ferricyanide with freshly prepared solution gives rise to a Turnbull's blue. Alright, you know that reaction, isn't it? Very popular reaction, like FeSO4 plus K3 FeCN taken 6 gives rise to Fe FeCN taken 6. However, you have to ensure that inside it is 3. Alright, because you can see inside it is oxidation number is 3, outside it is 2. This is very important. So you have to balance, right? Here 3 and here 2. So this is actually Turnbull blue. You know that if it is 3 outside 2 inside, it will be very famous Prussian book complex. That is not the question here. You can see that inside 2, that is potassium ferrocyanide, is treated with ferrous sulfate to produce a white PPT. Anyways, I borrowed the solution and I am directly writing it. Unfortunately, when I copied the question, maybe the solution will also come, and this is that white PPT which is formed. I want you to take up, but when it comes to the brown ring, very important, isn't it? FeH2O taken 5, NO plus 2 is that complex, and moreover that nitrosyl group is nitrosonium here, and iron oxidation state is +1, right? So this is that brown color precipitate. Hope you understood. What do you say? Alright, I hope you are following also. Alright, so go through these lectures, solve more such type of questions, and post your doubts in the form of comments. I'm going to answer them all. There are very few days left, and you're going to face the most interesting examination, most different examination, right? So be strong, try to read the question carefully. If you understand the question, you will get the answer. And don't try to attempt all the questions, and focus on strong areas or strong chapters. I'm going to finish this session in the next lecture. Until then, that's it.